33 Design Your Own Problem. The problem is currently shown on the screen, and I'm going to ask you to currently pause the video, read it over at your own pace, and try to solve it. And then after you attempt it, you can come back, unpause the video, and listen to our solution. Okay, so I think the first step to solving this problem is really visualizing what's going on. So I've drawn this diagram that's kind of a simplification of what's going on. But in any case, on our left here, we have this vertical light beam that's going to shine through this polarizer with angle phi. And this light beam is going to continue traveling to the right side here, where it's going to hit Throckmorton, who is currently sitting on this swing-like object, so which we can treat as a pendulum. Initially, this blue car is actually not here, but it's going to kind of appear there after Throckmorton has swung to the right side here. And then as Throckmorton is coming back down at maximum velocity, he's going to hit this blue roller coaster car in a perfectly elastic collision. And the blue car is going to roll to the left and then eventually fall off of this platform. So that's our visual for this problem, and now we're going to get into how we can actually solve these two parts. So first, we want to find the force that is actually applied to Throckmorton by the polarized light. And the equation that you see here, I equals I naught cosine squared phi, this is going to be Malice's law. And in this case, c is going to be the speed of light here. And we also know that the instantaneous force applied from this light on Throckmorton is going to be rho times A, and substituting rho in here, we can replace this with intensity times cosine squared phi divided by the speed of light multiplied by A. And since the problem did say that Throckmorton is going to be exposed for a length of time t, and the force is our constraint, our net force is going to be this expression right here. And following this, since we actually want to understand the motion of the pendulum itself, because we can kind of treat Throckmorton as very small in comparison to the swing, we can use the small angle approximation for a sign here. And we get that the restoring force is going to be negative mg theta. So putting these two pieces together, we're going to get our max angle theta max is going to be on this next page right here. So it's going to be I cosine squared phi divided by the speed of light times mg, all multiplied by A times delta t. And next we're going to first try to solve part A of the question, which is actually talking about the standing waves. So to do that, we first have to find the tension on the rope. We know that in a simple pendulum, this is going to be given as mg cosine theta, where theta is the angle the pendulum makes with the vertical. So at the position of least potential, when basically the pendulum is completely vertical, we have t equals mg. And at the moment of most potential, basically when Throckmorton is at his highest vertical point, we can just plug in our expression for theta max that we calculated earlier. Following this, we can actually apply the formula for the velocity of a standing wave on the rope. And just simply plugging in our tension here, we have our expressions for Vmax and Vmin given here. So that concludes part A. And the second part of the question actually asks how the collision is going to affect the roller coaster cart. So we first want to understand the collision. So using these energy equations, we can back into the velocity of the swing at the moment of maximum velocity. So essentially just setting this kinetic energy equal to this gravitational potential energy, and then solving for Vmax. We have an expression for Vmax in terms of gravity and sine of theta max. And now we can just simply apply the elastic collision formula for a non-moving object. And in this case, V2 is going to be the velocity of the object that was collided with, so it's going to be our roller coaster cart. So this formula, because it's quite easy to derive, you just have two equations, one for conservation of elastic energy, or kinetic energy, and one for conservation of momentum. Just kind of rearranging them, playing with them, we would obtain the formula given up above. And we can finally just apply this relationship to our context. So plugging in V2F, V1F, etc. Velocity 2 we obtain as this big looking formula, but we can just simply use this later because we're almost done with the problem. So we just want to find the time it takes the cart to hit the ground first. And then we can solve for distance with our constant acceleration kinematic equations. So this is going to be just a simple application of those equations here. And then finally plugging into the distance, we get that our answer is 2m over m plus m times the square root of 2g sine I cosine squared phi divided by cmg multiplied by a delta t, and then finally multiplied by the square root of 2hg. So that actually completes the end of the problem. I hope you guys enjoyed working through the problem and managed to learn something from working through it. And we also had a really great time coming up with this problem and then writing our solution. So we really enjoyed this process and hope to do it again in the future very soon.